Welcome to Lecture 5 of Discrete Mathematics. This is going to cover Predicate Logic Part 2. Okay, so in this video we're going to talk about nested quantifiers. We're going to talk about translating nested quantifiers to English, and from English to nested quantifiers, and finally, the negation of nested quantifiers. Alright, to start off, last time we saw singular quantifiers. So we saw the universal quantifier, which was written with this upside down A, and we saw the existential quantifier, which is written with that backwards E. So the universal quantifier, we read that as for all x, p of x is true, or it's true if p of x holds for all x. So this is our general statement. The existential quantifier is just guaranteeing that there's at least one x out there for which p of x is true. So for at least one x, p of x is true. True if p of x holds for some x. Okay. But this is the simpler case in predicate logic. In fact, there's many statements out there that need multiple quantifiers at once. Okay, and this is where nested quantifiers come in. So suppose we wanted to translate the following statement. And this is given to us in our everyday language. Okay, so for every action, there exists a reaction of equal and opposite magnitude. Okay, so this is a statement that's heard a lot in physics. Now, if we wanted to translate this into sort of logic-y English, we would say something like, for every action x. Okay, and I've got this here in red. We're going to see how that translates symbolically. That's our first piece. There exists a reaction y. That's in yellow. That's our second piece. And the last piece is such that their magnitudes are equal and opposite. Okay, so this is going to be that property that applies to these actions x and reactions y. And we're going to translate this like so. So we're going to use the universal quantifier for every action x, for all x. We're going to use the existential quantifier for there exists a reaction y. And we can put this property, their magnitudes are opposite and equal, as some function, propositional function m of x and y. Okay? Where the domains of x and y are defined as all forces. Right, so the forces in physics to which this applies to. So this is our first sort of combination of quantifiers. Okay, we're nesting this universal quantifier with this existential quantifier. And what this allows us to do is that it basically says that for everything in this domain, there's something, some y that goes with it. Okay. Let's look at example B. There is an algorithm that can solve every instance of this problem. Okay, so some problem that we have out there. Translate this to your logic English. There exists an algorithm X such that for every instance Y, X solves Y. So this time we're going to start off with the existential quantifier for the algorithm. We're going to use the universal quantifier for every instance y, right? So for all instances of this problem. And then we can just use some simple function, s of x, y, x solves y. Okay, so this is already the difference here between flipping these quantifiers in their order. Okay. And we're going to consider how the order of the quantifiers matters in a second. But let's just look at one last example. So in everyday English, we've got a sentence like this. There are people who are soulmates. Right now, here it's right away, it's not so easily determined, right, what our variables are or how many there are, but the assumption here is that we're talking about, say, just two people to start off with, right? So we translate this to a more logic-sounding English. There exists at least one person x, and there exists at least one person y, such that x and y are soulmates. So this is a case where you might want to use two existential quantifiers back to back. And then you've got your propositional function, s of xy, x and y are soulmates. Okay. Now let's consider the order of these quantifiers. Okay? Can they really be changed without changing the meaning of the statement? Okay, so let's consider the first case, the same quantifiers. So let's suppose we had two universal quantifiers. For all x and for all y, p of xy is true. And that is, in fact, the same thing as saying for all y and for all x, p of xy is true. Okay? Both of them translate to essentially the same message. For all x and y, p of xy. The same thing's true for two existentials. Okay? It doesn't really matter. You're just doing a kind of a one-to-one match. Okay? Both of these translate to, for example, there exist numbers x and y such that p of x, y is true, right? If the domain of x and y are numbers. So it does not matter what order you're putting this in, right? This is the same thing as that commutative property. Apples and oranges are the same thing as this oranges and apples, especially if they're in the same quantity, right? So when you have same quantifiers, they are in fact interchangeable. This has no effect on the meaning of the statement. But when we have different quantifiers, well, let's see what happens. So let's let our function L of xy mean x likes y. Okay, domain of x, domain of y, both are all people. So in the first case, let's say we wanted to use the universal quantifier, then the existential quantifier for our function L. What does this translate to? For all people x, there exists a person y such that x likes y. Okay? In everyday English, this just means everyone has someone they like. For all people, there's at least one person out there that they like. Now, what if we reverse the existential and the universal quantifiers? Now what happens? Okay, and notice I've got the same variables with them. I'm not even changing the variables, right? So the existential is still with y, the universal is still with x. In this case, they're all just still people, so it doesn't really make much of a difference. But how does this translate? Okay. There exists a person y such that for all people x, x likes y. Okay, now this is a different sentence. This is saying that there is some person y, a single person, that everyone likes. Okay, now this is all in reference to the same person. This is sort of like that algorithm example that we had before, right? There's a single algorithm that solves all problems. There's a single person here that everyone likes. Okay, so these are not necessarily the same sentence. In most cases, they're not translating to the same thing, right? The first one's just saying everyone has a person they like. That person does not need to be the same person for everybody, right? But in the second one, it does. Okay, so these statements are not equivalent. So in general, if you have different quantifiers, we do not consider them to be interchangeable. Okay? Let's look at some more examples. So let u be real numbers, and the propositional function xy mean x times y is equal to 0. So let's see if we can determine the truth values for each of the following statements with nested quantifiers. So we've got two universals. So we've got for all x and for all y, p of xy is true. Okay, so what this would translate to is that for all x and for all y, their product is 0. This is obviously a false statement, right? We can multiply two non-zero numbers, and their product will not be 0, or 2 times 2 is not 0, right? So it's a false statement. The second case, for all x, there exists a y such that the product of x and y is 0. This is going to be a true statement, that y is just 0. So we can multiply any number by 0, and yeah, their product is going to be 0. Okay? For the third one, there exists some x such that for all y, the product of these two numbers is 0. And again, that's true. It's just kind of saying the same thing as number 2 is, but now the x is the 0 in this case. Okay, so there does exist an x, that x being 0, such that for all y, if you multiply it by that x, the product will be 0. And finally, the last one says, well, there exists an x and there exists a y such that their product is 0. And this is also a true statement. In this case, either one could be 0. Okay, this is just saying that there's some specific combination of numbers out there whose product is 0. They could even both be 0 in this case, right? Now, what happens if we want nested quantifiers with compound propositions? How is this going to work? How does this look? So let's try translating the following example. So here we've got the universal quantifier out front, and this applies to this entire set of brackets. Inside the brackets, we've got the main operator, which is the disjunction. It's a disjunction of c of x, our first function, and a different quantified statement. We've got an existential quantifier, which applies to this inner parentheses, which is a conjunction. Now you've got c of y and f of xy. So let's see what these mean. So they've given us that c of x means x has a computer. And the same thing holds for c of y. It just means y has a computer. Okay. Then we've got the function f. F of xy means x and y are friends. And the domain U for both x and y is all students in your school. Okay? So the way we're going to go about this is for all students in your school, right? Or for every student in your school, either they have a computer. Okay, so every student in your school has a computer, or there exists another student, okay, who has a computer and is friends with X. Okay, so to put that into more plain English, every student in your school has a computer, or they have a friend who has a computer. Okay, so this conjunction between these two properties, they have a friend who has a computer. In logic, we would just say there exists a person who is both their friend and owns a computer. It's the same idea. Okay, so every student in your school has a computer, or they have a friend who has a computer. So this is an example of how you might see nested quantifiers with compound propositions. Okay, and finally the last topic that I want to cover in this video is negating nested quantifiers. So do a quick review. We have De Morgan's laws from propositional logic, and these involve negations of conjunctions and disjunctions, and this is how they went. And the same ideas from propositional logic apply to functions. These are propositional functions. Okay? So these are just rules about connectives, and they're going to work just the same way as they did before. So the negation of a conjunction is the same thing as the disjunction of both negated functions, right? So it's almost like we're distributing that negative again, and the sign is flipping. Same deal for rule number 2 here. Negation of a disjunction is the same thing as the conjunction of negations. Distribute that negative, flip the sign. Now, we also saw in the last video 2 new De Morgan's laws for quantifiers. Okay, so rule number 3 was talking about the negation of the universal quantifier on some function p of x. This is equivalent to the existential quantifier of the negation of p. Okay, so this translates to something like, it is not the case that for all x, p of x. Okay, so if p of x was something like, in the last example, x as a computer. So it is not the case that for all students, the student has a computer. In other words, there are some students who do not have a computer. Okay? So there's just 2 different ways of saying the same things. Not all students have a computer, or some students do not have a computer. And rule number 4 is similar here. So this is saying it is not the case that there exists even one student with a computer. In other words, it's the same thing as saying it is true for all students that none of them have a computer. Okay, so these were our De Morgan's laws up until now. So let's make use of these for the following example. Okay, so we've got a compound proposition here with nested quantifiers. When we just want to simplify this, we just want to distribute that negation, and we want to see what happens to this function. How does this function sort of translate into an equivalent statement as we do so? Okay, so by our new rules 3 and 4, we can push the negation through each of these quantifiers, but we have to make sure we flip them. Okay? So the negation of the existential is the same thing as the universal quantifier of a negation. Okay, so the universal quantifier of a negation of all this now. Same deal for the next one. Now, we've got a universal. We're going to push that through. That should become an existential quantifier now. And for the last one, negation of an existential is again going to become universal, and then that negation is going to be now in front of our propositional functions. Okay, and now from here, we're just using our old school De Morgan's law, number 1, negation of a conjunction. We're going to distribute this to both parts of the conjunction, and that conjunction is going to become a disjunction. Okay, so for that original statement, it was the negation of the existential of x, the universal of y, the existential of z, of p and q. And this has become the universal of x, the existential of y, the universal of z, and the negation of p or the negation of q. Okay, so this is just a quick example of how we can use the rules of equivalence to push through that negation. Alright, so this has been Predicate Logic Part 3. These were nested quantifiers. We'll pick up from here in the next video. Thank you for watching. If you found this video helpful, please like and subscribe to the channel for the next video. Thank you.